Welcome back. We will continue with the binary independent variables, but in this video, we will focus on the interaction terms. Sometimes, it is natural to have the scenario that the partial effect of an independent variable xj on y also depends on another explanatory variable xi. In other words, beta j is different for different xi. If the independent variable xi is binary, it means the partial effect of xj on the dependent variable y differs across different groups. For instance, suppose we want to estimate the marriage premium on wage, we can use this econometric model. The dependent variable is still the wage. For the independent variables, we now have a new binary variable, married. It equals to 1 if the worker is married, and it is 0 if the worker is single. The parameter gamma 0 is the marriage premium. If gamma 0 is larger than 1, then the average wage for those who are married will be higher than those who are single when all other factors are being controlled for the whole population. Suppose we believe that the marriage premium is different for males and females. In other words, this gamma 0 is different for the female group and the male group. How can we test this hypothesis? One approach is to generate new dummy variables like we did for ordinal variables. Basically, there are 4 groups: single male, single female, married male, and married female. We can choose a base group, then create 3 additional dummies for the other 3 groups. Then the parameters for each one of these 3 new dummies measures the difference for the average wage compared to the base group when all the other variables are being the same. Here we introduce another approach. That is, we add an interaction term for the female and married in the model. Notice that this female dummy and the married dummy has already been included in the model. If the female dummy is 0 and the married dummy is also 0, we have the intercept beta 0 for the single male. Similarly, we have the intercept beta 0 plus delta 0 for the female but single, beta 0 plus gamma 0 for the married male, and lastly, the intercept for the married female is beta 0 plus delta 0 plus gamma 0 plus rho 0. You can also try to write down what's the intercept for different groups if we adopt the first approach, that by creating 3 new dummy variables. Fundamentally, these 2 approaches are the same, but the representation for the slopes are different. By using the interaction term, we can easily test the null hypothesis, like whether the gender difference depends on the marriage status or not, or equivalently, whether the marriage premium are different for different genders. Let's check the regression results with an interaction term, and this interaction terms is a binary variable, female, times another binary variable, married. The constant intercept is an estimate for the true parameter beta 0. Similarly, the coefficient for female is to estimate delta 0. The coefficient for married is to estimate gamma 0. And the coefficient for the interaction term is for the estimate of rho 0. Given these coefficients, we have the intercept estimate for each one of the groups. The base group here is the single male, and the intercept is beta 0 hat equal to 0.388. The intercept for the single male is beta 0 hat plus delta 0 hat, and it is around 0.291. The intercept for the married male is beta 0 hat plus gamma 0 hat, which is around 0.68. And lastly, for the married woman, the intercept is the sum of all these four coefficients, which is around 0.267. Now we can check different hypotheses. For instance, suppose the hypothesis is that there is no marriage premium for male, then the non-hypothesis should be that gamma 0 equal to 0. Because this gamma 0 is the difference for the intercepts for the single male and the married male, if gamma 0 is equal to 0, then there is no marriage premium for the males. If we check the t-statistic for the gamma 0 hat, we can see that it is significantly different from 0. Suppose now the non-hypothesis is that there is no marriage premium for female, then we need to compare the intercepts for the married female and the single female. So the difference for the coefficients is gamma 0 plus rho 0 equal to 0. Here is the linear hypothesis test in R. The H0 is gamma 0 plus rho 0 equal to 0. The p-value is quite large, so we cannot reject the non-hypothesis that there is no marriage premium for female. So far, we discussed examples to allow intercepts to differ for any number of groups. We can also interact a dummy variable with continuous explanatory variables. For this case, then we allow for the slopes of the continuous variable to differ by different groups. Continuing with the wage example, suppose that we wish to test whether the return to education is the same for male and female. We need a model that the parameters of education are different for male and female workers. Consider the following model. We already included a dummy variable for females to allow for a constant wage difference between two groups. In addition, we also add the term delta 1 times the female before the independent variable education. With the interaction terms that a dummy variable female and the continuous variable education, this model allows that the marginal return for education is different for male and females. If the dummy variable equal to 0, then we will have the population regression function for male workers. The intercept for the population regression function is beta 0 and the slope is beta 1. But if the dummy variable is equal to 1, we will have the intercept for females equal to beta 0 plus delta 0, and the slope is beta 1 plus delta 1. Different values for delta 0 and delta 1 will have different policy implications. For instance, here is the graph for the population regression model. If the education level is equal to 0, the intercept for male is beta 0, and the intercept for female is beta 0 plus delta 0. For this graph, delta 0 is negative, which we already see that in previous examples. There is a gender wage gap, even the education level for male and females are the same. Besides this fixed amount of wage difference for any level of education, the marginal return for education is also different for men and women. Here, the slope for men's education is beta 1, but the slope for women's education is beta 1 plus delta 1. If delta 1 is also negative, it means the gender wage gap will expand for higher education. However, if delta 1 is positive, then the slope for women's education is higher than men's education. One additional year of education will increase women's wage more than men's wage. If we know the marginal return for education is higher for female than for male, then we may probably make policies to encourage female education in the hope to reduce the gender wage gap. But if otherwise delta 1 is negative, then the education-oriented policy will just make the situation of gender wage gap worse, because males will benefit more from such type of education policies than females. How can we test whether delta 1 is positive or negative? We can run the following econometric model. This model is the same as the before, but the term delta 1 times the female is taken out of the slope for education. Notice that this interaction terms is equal to 0 for all male in the sample, and it equals to the level of the education for all female in the sample. Suppose the hypothesis is that whether the return to education is the same for women and men, then we are basically asking whether the slopes for two different population regression functions are the same or not. Notice the difference for these two slopes is beta 1 plus delta 1 for female minus the beta 1 for male is equal to delta 1. So the null hypothesis is delta 1 equal to 0. We can observe that this null hypothesis is a single hypothesis. We only care about the difference between two slopes. We do not care about the intercept delta 0. Suppose the hypothesis we are interested in is, are women and men with the same level of education paid the same or not? In this case, besides the marginal return for the education, we also care about the intercepts, because the intercepts captures the difference in the wage between two groups for any level of the education. For this case, the null hypothesis is a joint hypothesis. It says that delta 0 equal to 0, which is the constant difference between these two groups, and the delta 1 equal to 0, which means the slope difference for these two groups. We similarly use the dataset wage 1 and run the regression. Besides gender and education, I also control the experience square, tenure, and tenure square. First, let's check the estimator for the marginal return for education for male and females. The coefficient for education is the return to education for men, which is around 0.2%. The marginal return of education for female is beta 1 hat plus delta 1 hat, which is around 7.6%. The t-statistic for delta 1 hat is quite small, so we cannot reject the null hypothesis that delta 1 equal to 0. The size of the coefficient is also very small. So we can say that the marginal return of education for female and males are neither economically significant nor statistically significant. Interestingly, if we check the intercept difference, delta 0 hat, on average, females earn 23% less than males when all other factors are holding the same for these two groups. But now it's not significant anymore. This is because we added interaction terms, and now that the coefficient is much less precisely estimated. By adding interaction terms, you kind of reduce the observations for a specific group. And it often will increase the standard error and making the coefficient less likely to be significant. But for this case, since the size is quite large, we still call that there is gender wage gap in terms of the intercept because the coefficient is economically significant. For the joint hypothesis that women and men with the same level of education will have the same payment, we test this joint hypothesis in R. The null hypothesis is that the parameter for the binary female delta 0 equal to 0 and the interaction term for the female and education delta 1 equal to 0. The p-value for the joint hypothesis is very small, so we can reject the null hypothesis that delta 0 equal to 0 and delta 1 equal to 0 at very small significance levels. This hypothesis test shows that females do not have the same level of wage as males, even though they have the same level of education and all other variables are also controlled for.